Okay, in last class, I gave you this problem. Anyone have you solved? Hmm? Have you solved or do I need to discuss it here?
So it would be better if you can discuss.
Okay.
It's a salt.
Who is this?
It's a Siddharth.
Siddharth. Okay. Okay. So can you tell me what you can conclude after solving this problem?
Sir, the effective resistance on high and low side, they came like same, they came. And same for the
Yes.
impedance thing.
So any advantage you have got? Uh, I mean, you have noticed of using this per unit system?
So like for this particular question, it is only told to find like the effective resistance. So for the advantages part, I have not thought, but I got these two same. So I think that will help in calculation. Like it will make the calculation easier, I guess.
Okay. Okay, let us see what advantage we can get. Okay, so a single phase transformer is given with ratings 10 kVA, 2000 by 200 volt. So these are the voltage ratings. High voltage side 2000 volt, low voltage side 200 volt, and power rating is 10 kVA. And the parameters are given: high voltage side resistance 3.6 ohm, high voltage side reactance 5.2 ohm, low voltage side resistance 0.04 ohm, low voltage side reactance 0.056 ohm. Okay. The question is to find the per unit values of REH, XEH, REL and XEL. That means you have to calculate the equivalent resistance from high voltage side, from low voltage side, as well as you have to calculate the equivalent reactance from both high voltage side and low voltage side. Okay, that is the problem. So let us consider the high voltage side first. So for high voltage side, base voltage, that would be 2000 volt. So VBH 2000 volt. Base current you have to calculate using this power rating and voltage rating. So that is 5 ampere. Now you can calculate base impedance, that is VBH by IBH, which is 2000 by 5 ampere, or you can directly calculate this using another formula. So what was that formula to calculate this ZBH? Alternative formula?
Sir, voltage on high voltage side whole square by rated VA.
Yes. So you can apply 2000 square divided by 10 kVA, so 10 into 1000. From that you also can calculate this ZBH. Okay. So this is 400 ohm. So base impedance of high voltage side is 400 ohm. So with respect to this 400 ohm, you have to calculate REH and XEH. Okay. Now RH per unit is equal to 3.6, this actual value divided by the base impedance, so 400, that is 0.009, and XH per unit, that is 5.2 divided by 400, so you will get 0.013. That is very simple. Only you have to calculate the per unit values of the high voltage side parameters RH and XH. Okay. Next, you have to calculate the REH. REH means equivalent resistance referred to high voltage side. Okay. So REH referred to high voltage side can be calculated using this formula, that is high voltage side resistance plus low voltage side resistance referred to low voltage side. Okay, so here we are considering the high voltage side as the primary side and low voltage side as the secondary side. Therefore N1 by N2 is actually this 2000 by 200. Okay, so we can apply this formula to calculate REH. So REH is equals to 7.6 ohm. Okay, so 7.6 ohm is the actual value of REH. Now here the question is to calculate the per unit values of REH. So you have to divide this 7.6 by this 400 base value. Okay, then you will get this REH per unit. So therefore REH per unit is equal to REH actual value divided by base impedance, which is 7.6 divided by 400, then you will get 0.019. Is it clear up to this?
Yes, sir.
Okay, now you have to calculate XEH, same formula, same process. So tell me what is the value of XEH per unit. First of all, calculate XEH using this formula, that is XEH is equal to XH plus XL into N1 by N2 whole square. Then you will get the XEH actual value, then divide it by 400. So tell me what is XH per unit, XEH per unit. That means equivalent reactance referred to high voltage side in per unit value.
So 2.7 into 10 to the power minus 2.
0.27 027.
0.027.
Yes.
Okay with everyone, this calculation?
Yes, sir.
So we have got REH and XEH. Now calculate REL and XEL. So you have to calculate the low voltage side parameters. So for low voltage side, base voltage 200 volt, base current you have to calculate, and then calculate the base impedance for low voltage side, or you can apply the other formula, that is 200 square divided by 10 into 10 to the power 3. In both way you will get the base impedance as 4 ohm. So for ZBL calculation, if you use the voltage and power rating, then you don't have to calculate the base current. Okay. So now you have got base impedance, so you will be able to calculate RL and XL in per unit value. So calculate those. RL in per unit and XL in per unit. Now calculate REL. So REL will be RL plus RH. Now you are referring to the secondary side, that means low voltage side. So N2 by N1, that is 200 by 2000 will be the turns ratio. So actual value of REL is 0.076 and per unit value is this actual value divided by 4. So we will get 0.019. So this is the per unit value of equivalent resistance referred to low voltage side. Now similarly calculate XEL per unit.
So 0.027.
Let us see. Yes, 0.027. Now, note one thing, that in calculation of REH, XEH, REL and XEL, we have not used these values, RL per unit, XL per unit, or RH per unit, or XH per unit. We have not used. So why we have calculated this? This I have calculated to show you something. So what is that? To note that RH per unit is equal to this 3.6 divided by 400. XH per unit is equal to 5.2 by 400. Sorry, it is 0.013. RL per unit equals to 0.04 by 4 equals to 0.01. That means actual value by base value, and XL per unit are these. Okay. Now note this thing. REH per unit is equal to REL per unit, that is equal to RH per unit plus RL per unit. That means you have to add these two to get total equivalent resistance referred to either side, either high voltage side or low voltage side. Both these per unit values are equal, and you don't have to refer. See, you are not referring.
Yes, sir.
And XCH is this. So is it advantageous if we use these per unit values?
Yes, sir.
So that means you don't have to use this formula. So how will you solve this problem? Simply calculate this base value using either of these two formulae as I have mentioned. So then calculate this value and this value. After that, calculate this value and this value. Then apply this formula. Then all this value will be calculated. Got my point, everyone?
Yes, sir.
Yes, sir.
You
Sir, in
don't have to.
every case, REH per unit and REL per unit are equal.
Yes, it will be equal always. That is the benefit of using per unit system. Okay. Okay, next. So we have completed this per unit representation of transformer parameters. Next topic is voltage regulation of transformer. So first of all, what is voltage regulation? It is defined as the change in magnitude of the secondary terminal voltage expressed as a percentage or per unit of the secondary rated voltage when load at a given power factor is reduced to 0 with the primary applied voltage held constant. So basically it is the change in terminal voltage expressed in terms of secondary rated voltage. Okay. So and what is the condition when there will be this change in terminal voltage? If you reduce the load connected to this secondary side to 0. So let us consider that this, when there is some load is connected across the secondary side, the terminal voltage is Vt. Okay. and when this load is reduced to 0, this voltage will increase normally, because normally the loads are inductive in nature. So this terminal voltage will increase, and let us consider that voltage be V0. Okay, so V0 is greater than Vt. So you have to calculate the change in terminal voltage, that is V0 minus Vt, and you have to take the percentage or per unit of that change with respect to rated voltage, rated secondary voltage. So what will be the rated secondary voltage, that we will see later on. So let us consider that rated voltage be Vr. So you have to divide this change in terminal voltage by Vr, and then this value is in per unit. If you multiply it by 100, then you will get percentage voltage regulation. Now what is is there any other condition? Yes, the condition is that you have to keep the power factor fixed. Okay, that means this load connected to the secondary side, which you are removing from the transformer, okay, transformer secondary, that load has to be defined with a given power factor. And the when you are removing this voltage, this load from the secondary side, the primary voltage has to be kept constant. Suppose the primary voltage is V1, this has to be kept constant. Okay, so these are the conditions while defining the voltage regulation. Is it clear? So don't tell just that it is the change in terminal voltage with respect to the secondary rated voltage. That is not the full definition. You have to mention the conditions also. Otherwise, the definition will be wrong. Is it clear? Any doubt?
Sir, how to maintain the power factor constant?
No, you don't have to keep it constant. You have to define the load for a given power factor. Suppose you have connected some load which is having 0.8 lagging power factor. That is defined. You don't have to keep it fixed. If you remove the load, then there is nothing is connected to the secondary side. So no question of power factor. So you cannot keep power factor fixed. I am not saying that you have to keep power factor fixed. You have to define the load for at a given power factor. That is what I was saying. Okay.
Yes, sir.
Any other question? Okay. Now let us see how to calculate this voltage regulation using the transformer parameters. That means the output voltage, secondary output voltage or secondary voltage, primary voltage, and the rated secondary voltage. What is this rated secondary voltage? Let us see. So let us assume that V2 is the secondary terminal voltage at any load. At any load means at any given load with a given power factor. That is how the load is defined. Okay. Next, E2 is the secondary terminal voltage at no load. Recall the circuit diagram, either this schematic diagram or equivalent circuit. If there is no load connected across the secondary side, then V2 is 0 and the terminal voltage across this open circuit condition is the secondary induced EMF, that is E2. Okay. So when load is removed, the secondary terminal voltage is E2. Then at a given power factor and specified load, the voltage regulation is given by voltage regulation VR is equal to E2 minus V2 by secondary rated voltage. Okay, this is in per unit, and as per standard, the secondary rated voltage of a transformer is equal to the secondary terminal voltage at no load. That means E2 is actually the secondary rated voltage. Okay, so it is the convention to state that this secondary terminal voltage at no load will be the rated voltage. That means the nameplate data. Okay. So now the equation, the previous equation modifies to this, that is VR equals to E2 minus V2 by E2. So here V2 is the terminal voltage at a given at any load with a given power factor. E2 is the secondary no load voltage, and this E2 is the secondary rated voltage, which is same as that of secondary no load voltage. Okay, so this is in per unit. If you multiply it by 100, you will get percentage voltage regulation. That is how you can calculate the voltage regulation of a transformer if you are able to measure V2 and E2. If this V2 and E2 are measurable using any measuring device, okay, then you can apply this formula to calculate voltage regulation of a given transformer. Okay, now normally the voltmeter ranges are from 0 to 600 volt. Maximum, if you use some multimeter, it can be 0 to 1000 volt. So above 1000 volt, it is very difficult to measure using any measuring device. Okay, so any transformer having voltage rating greater than this range, then how will you calculate voltage regulation using this formula? So it is not possible to calculate, because in that case this V2 and E2 are not measurable quantities. Okay, so at no load the primary leakage impedance drop is almost negligible. Therefore the secondary no load voltage, this primary secondary leakage impedance drop is negligible. Therefore the secondary no load voltage is equal to E2 is equal to V1 into N2 by N1. Actually the formula was V1 by V2 is equal to N1 by N2, or E1 by E2 is equal to N1 by N2. Okay, so E2 is equal to E1 into N1 by N2. That means E2 is equal to E1 into N2 by N1. Okay, now if the leakage impedance drop is negligible, in that case this E1 becomes V1. Okay, then only we can write this expression. Is it clear?
Yes, sir.
So using this expression of E2, we can modify this equation, that is VR is equal to, putting the values of E2 here and here. So V1 into N2 by N1 minus V2 by V1 into N2 by N1, and after simplification, just a minute, after simplification you will get this expression, that is V1 minus V2 into N1 by N2 divided by V1. So V2 into N1 by N2, what is this? This is actually the secondary voltage referred to primary side. Okay. So again you have to measure the applied voltage V1 as well as the output terminal voltage, that is voltage across the load V2. Okay, so for higher rating machines, that means transformer, those quantities may not be measurable quantities. So in that case we need one indirect method to find the voltage regulation of a transformer. Okay, for small transformers for which this V1 and V2 both are measurable quantities, we can apply this formula or even this formula, because if we do not connect any load to the secondary side, then we can measure E2 easily. Okay, we can measure E2 as well as V2 for a given load. Okay, so using this formula we can calculate this voltage regulation, or we can calculate this equation, calculate voltage regulation. So the condition is this V1, V2 has to be measurable quantities. Okay, so for larger transformers having higher ratings, we need one indirect method or some analytical method, we can say. So here let us see this method, determination of voltage regulation. So here, to determine the voltage regulation, the approximate equivalent circuit referred to primary side or secondary side can be used. Approximate equivalent circuit means we have neglected the the parallel branch. That means the exciting current is neglected. Therefore, the parallel branch parameters, that is RC and XM, are not included in the equivalent circuit. Okay, so this is the equivalent circuit referred to secondary side, neglecting the parallel branch parameters. Okay, so here RE2, what is this RE2? RE2 is equal to R2 plus R1 into N2 by N1 whole square. R2 is the secondary side resistance, R1 is the primary side resistance. Then if you multiply it by trans ratio square, then you will get the referred quantity. Then RE2 is the total resistance or equivalent resistance referred to secondary side. Same is applicable for XE2 also. Okay, so this is the equivalent circuit referred to secondary side when the exciting current is neglected, and for that we have not included the parallel branch, that is RC and XM. RC is the core loss resistance, XM is the magnetizing reactance. Okay, now can you draw the phasor diagram for this equivalent circuit? Anyone? For this equivalent circuit, you have to draw the phasor diagram. First of all, tell me the equation, KVL equation.
Sir, E2 minus I2 whole into RE2 plus JXE2 is equal to
E2
V2.
minus, or you can write E2 is equal to V2
I2
plus I2 whole into RE2 plus JXE2.
JXE2.
Okay. Now for this equation, can you draw the phasor diagram? Taking lagging power factor. That means I2 will lag V2 by some angle, suppose theta 2. That is what I was saying in previous classes, that you have to know how to draw the phasor diagram for any given load, that is either lagging load or unity power factor load or leading load. Okay, then you have to know how to modify those three equivalent circuits for any other given condition. Okay, so here you can see all the parameters are referred to secondary side and no primary quantities are shown in this diagram. Okay, that is the primary quantities, that is R1 and X1, those are referred to secondary side. So we have only this circuit, and for this secondary side we have only this equation. So for this equation only, how to draw the phasor diagram? First of all, draw V2 and along the positive y direction, that means vertically upward. Then draw I2 lagging it by an angle of suppose theta 2. Then draw I2 RE2 from V2 and it is in parallel with I2. Then draw I2 J I2 XE2 in quadrature with I2
I2.
or I2 RE2. Okay, then join the starting point of V2 and the end point of J I2 X2, then you will get E2. Simply this diagram. This is I2, this is V2, this is I2 RE2 which is in parallel with I2, then in quadrature with I2 or I2 RE2 is J I2 X2, and then join this point and this point, you will get E2. I have drawn some other things also, those are not required till just now. Just try to draw the phasor diagram based on this equation or this equivalent circuit. Then we will draw the other things. Okay.
Yes, sir.
So the phasor diagram is, first of all draw V2 along positive y axis, then draw I2 lagging V2 by an angle of theta 2, then draw I2 RE2 in parallel with I2 and J I2 X2 in quadrature with I2 or I2 RE2, and then draw the starting point of V2 and end point of J I2 X2. These 2 points, then you will get E2. And that this phasor diagram also satisfies this equation, E2 is equal to V2 plus I2 RE2 plus JX2 JXE2. Okay, so this is for lagging power factor. V2 is leading I2 or I2 is lagging V2 by an angle of theta 2. Okay, now we will use this phasor diagram for the calculation of voltage regulation. So let us consider this magnified view. So to calculate voltage regulation, first of all, take an arc with draw an arc taking radius OD. OD means E2. Okay, so draw an arc. This is the arc, and extend OA, that means V2, which will intersect with this arc at point F, which means OD is equal to OF because they are the radii of same circle. Okay, now draw one perpendicular from this point on this extended line, that means extended line of OA, that means on AF we can say. So that point is B, and then draw another perpendicular DC dashed, which is drawn on BC and it is extended up to this point C dashed, and join this C dashed and B dashed, making B dash C dashed parallel to BC. So this line and this line are parallel. Is it clear?
Yes, sir. Yes.
Yes, sir.
So OD and OF are equal, so we can say this OC, this length is approximately equal to OF, because this length is very small. Okay, so we can write E2 is approximately equal to OC. Actually, E2 is equal to OD, which is equal to OF, which is approximately equal to OC. Right?
Yes, sir.
Now OC is equal to this length OA, then this length AB, and this length BC. Right? Now this BC is equal to B dashed C dashed. This length and this length are equal, so we can write this E2 is equal to OA plus AB plus B dashed C dashed. Now OA, that remains same. Now AB, this length, this length AB, what is it? This is the cosine component of AB dashed. This angle is theta, because this angle is theta. This line and this line are parallel, and this is the transversal, so this angle and this angle are same. Is it okay with everyone?
Yes, sir.
So AB dashed cos theta 2 is equal to AB. So in place of AB, we can write AB dashed cos theta 2. Because why we are changing from AB to AB dashed cos theta 2? Because only this length and this length are known to us. This B dashed D and AB dashed, and also OA. These are the known lines. Okay, but we can see E2 is equal to OC. So AB and BC are not known. So we have to express them in terms of these known lines, known lengths. Okay, so that is why we are converting. So AB is equal to AB dashed RE2 I2. Sorry, AB dashed cos theta 2 and B dashed C dashed, this length. Now to find B dash C dashed, consider the triangle D B dashed C dashed, this triangle. Okay, so now consider this triangle. So this is 90 degree. Why? Because this B dashed D, this is in quadrature with this line or this line. So if this angle is 90 degree, so this angle is 90 degree. Okay, now consider this triangle ABB dashed, ABB dashed, that is also right angle triangle whose this angle is 90 degree. So if this angle is theta 2, so this angle is 90 minus theta, so obviously this angle will be theta 2. Is it clear?
Yes, sir.
Angle DB dashed B, this angle is equal to theta 2. Is it clear with everyone? Any doubt?
No, sir.
Now if this angle is theta 2, then this angle will be theta 2. Why? Because this line and this line are parallel, and this is the transversal DB dashed. So this angle is theta 2. So when this angle, if this angle is theta 2, then we can express this side and this side in terms of this side. One is cosine component, another is sine component. So this side is cosine component and this side is sine component. Okay, so therefore this B dashed C dashed is actually DB dashed, that means this line into sine theta 2. Again we are expressing this B dash C dash in terms of this length I2 XC2, because that is the known length. Am I clear?
Yes, sir.
So now we can put the values of AB dash and DB dash. So we can write this OA, that is V2, AB dash is I2 RE2 cos theta 2, and DB dash is I2 XE2 and with it sin theta 2. Okay. So now we have E2 is equal to V2 plus I2 RE2 cos theta 2 plus I2 XE2 sin theta 2. Now recall the expression of voltage regulation. It was E2 minus V2 by E2. So first of all, from this we can calculate E2 minus V2. So therefore the secondary voltage drop E2 minus V2, that is equal to I2 RE2 cos theta 2 plus I2 XE2 sin theta 2. And if we divide this by the secondary rated voltage, which is E2, then we will get the voltage regulation. So therefore voltage regulation is equal to E2 minus V2 by E2. So we have to divide this expression by E2, then we will get the voltage regulation. Now the question is, can we calculate voltage regulation using this expression?
Yes, sir.
No. If
Theta 2 is
I2
not
and I2 and E2 are not measurable, then still we cannot use this expression. We need something more, isn't it?
theta 2 we don't
So
know.
Sir,
sorry.
I2 by E2 is equals to Z2.
Yes, if this E2 and I2, if this current I2 is rated current, then only we can replace that by Z2. If and that Z2 is actually base impedance, so R2 by Z2 will be per unit resistance and XC2 by Z2 will be per unit reactance. So that we so we need further modifications. So if I2R is the rated current, so R means rated, okay, then I2R RE2 by E2, that is voltage drop across RE2 at rated current divided by rated voltage, which is actually the per unit equivalent resistance or per unit resistance drop. Why is it so? Because this E2 by I2R, that is ZB, base impedance. Okay, so E2 by I2, that is ZB, so RE2 by ZB, that is RE per unit resistance, and that is denoted by the symbol epsilon R. Similarly, I2R x E2 by E2 is equal to epsilon x, which is equal to per unit equivalent reactance. So this is per unit equivalent reactance. So if we know the per unit values of resistance as well as reactance, then we will be able to calculate the voltage regulation of a transformer for a given load, and given load means the power factor has to be mentioned. Okay, given load at a given power factor, then only we can calculate the voltage regulation using this formula, and it is applicable to all transformers. Okay, so therefore voltage regulation equals to epsilon R cos theta 2 plus epsilon x sin theta 2. So using this equation we can calculate the voltage regulation of a transformer for lagging power factor load only. For leading power factor load, this sign plus sign will be negative. This you can check drawing the phasor diagram for leading power factor, then applying the same logic. Okay, first of all draw the phasor diagram for leading power factor, that means V2, I2 will lead V2, then approaching same way you will get this expression. For leading power factor load, voltage regulation is equals to epsilon r cos theta 2 minus epsilon x sin theta 2. Any question up to this? No. Okay. Now, condition for zero voltage regulation. So, what will be the condition? For that, we will get zero voltage regulation. That means there will be no change in terminal voltage. So, if load power factor is varied with constant values of load current and secondary EMF, then zero voltage regulation will occur when this epsilon r cos theta 2 plus epsilon x sin theta 2 equals to 0. So, what is the condition? You have to keep constant the load value, that means the magnitude, but you have to vary the power factor. Okay, that means if you change the power factor from uh, inductive to capacitive, then there will be some point at which this voltage regulation will be 0. So, voltage regulation 0 means epsilon r cos theta 2 plus epsilon x sin theta 2 equals to 0. From that we can get that tan theta 2 is equal to minus of Re2 by Xe2. That is the condition, and the magnitude of load power factor, from this we can calculate the magnitude of, that means the relation tan theta 2 is equal to minus of Re2 by Xe2. From this relation we can find this relation also, that is cos theta 2 equals to Xe2 by Ze2. So, at this value of power factor, the voltage regulation will be equal to 0. That means there will be no change in power factor, no change in terminal voltage if you remove the load from the transformer. Is it clear? Any question or any doubt? Okay, time is almost over. Okay. Okay, today up to this condition for maximum voltage regulation.
Sir, can you please